Thanks everyone for joining us today in this webinar on the topic process simulation in robotic additive manufacturing. This is the second webinar of a series of 3. So the first webinar was on path planning, and the third one will be on real-time monitoring. So this webinar is organized as part of the Softdream project funded by the EIT Manufacturing. My name is Anne Carway, and I'm working as a project manager for Aerospace Valley, a French innovation cluster specialized in aeronautics, drones, and embedded systems located in southwest of France. I will be today the moderator for this webinar. So just first, I will present you how this webinar will work, some technical information. So all the attendees' microphones are muted to avoid any background noise. To ask questions, you can use the following icons shown here on the slide. And if this icon is not available, you can send me as well directly your questions and my email address shown here. And we will have some time at the end of the webinar to answer them. So if you have questions at the end of the webinars, you can as well contact the speakers. You will have their email address in the next slide. And of course, as well, this webinar is registered, and the presentation as well will be available in 48 hours after this webinar. And you will receive the links directly on your email address. So now just for the speakers today that we have with us. So the first speaker is Emil Johansson. He is a research scientist in additive manufacturing at the Research Institute of Sweden. He has an extensive experience in materials and process development, and is currently working on robot-based additive manufacturing of large-scale thermoplastic and short fiber composites, and is as well the coordinator of the project Softdream. Today, the second speaker will be Sergio Costa. He is a research engineer specialized in structure analysis and modeling for composites at the Research Institute of Sweden as well. He has a PhD in solid and structural mechanics, covering the development, improvement, and validation of crash model for composites. More recently, he has been involved in simulation projects, including multi-physics phenomena such as additive manufacturing of polymeric materials. And the last speaker today will be Fabien Poulain. He's a research engineer specialized in 2 processes, in the WAM and in the wire-based laser metal deposition process at the French Institute of Technology, STIA. He has a PhD in mechanical engineering and is now currently working on thermal simulation and on improving mechanical and metallurgical properties for those 2 processes. So I will now leave the floor to our first speaker, and we can have an overview of the agenda as well. So what if Softdream, who will be presented by Emil Johansson. We will now go after to the motivation for process simulation and the simulation of thermal history with Sergio. And at the end, we will speak about automated model calibration for metallic AM process simulation. And we will see the manufacturing step definition based on distortion estimation with Fabien. So now I leave the floor to Emil for the project presentation.
Thank you, Anne. So I will show my screen. Okay, now my screen should be shared. Thank you, Anne, for that introduction. My name is Emil Johansson. I am the leader of the innovation project Softdream, which is funded by EIT Manufacturing. And this project was started about 10 months ago now, based on a number of industrial challenges that we saw within additive manufacturing, primarily of large-scale parts, such as product personalization, the possibility to do mass customization, on-demand and on-site manufacturing. And we saw that, of course, you have rigid production systems typically in the industry, but even with 3D printing, it's typically associated with high cost and long lead times if you're talking about very large parts and complex parts. Industrial robots can solve many of the current limitations that we see in 3D printing. You have scalability, for example, both large and small parts. You have flexibility with the robotics, where it's possible to put them into production or use them for prototyping, and in lots of different materials like concrete, thermoplastics, composites, metals, for example. And the cost of a robot is by comparison quite low. But what we saw is that there is currently a lack of software, making it very easy to use the full flexibility of robots for 3D printing. And by that, I mean anything from the design simulation, process planning, and monitoring that you might want to do when you're printing parts using industrial robotics. So what we are developing in our innovation project is a set of tools to solve these problems, which we will make available through our cross-platform API to help users of robotic additive manufacturing succeed as well as possible. And it involves design simulation tools. The simulation, of course, we will talk more about today, but also process planning with some possibilities to do advanced toolpath planning. One aspect is, of course, very important, which is the real-time monitoring and also process feedback. So we have functionality for that. And the idea is to make this available through a very generic and customizable interface so that you can use it with different robots, different materials even, in different settings and different numbers of robots as well. And this overview here shows a little bit of what we are trying to achieve. So we have this functionality that you can see on the right with, for example, path planning or process simulation. And we make that available through a number of different ways, like our Python bindings, C++ SDK, or our REST API. So that, for example, if a user who is very advanced in the path planning but wants to use the real-time monitoring interface, they can just choose to use this part of our proposed solution. And to show you a little bit about what this looks like in real life, this is a view of our user interface as it looked like about a month ago, where we have the possibility to configure different types of robots with different types of process tools. This is an extruder for thermoplastic and composites, for example, and use that to generate advanced toolpaths like this, for example, non-planar toolpath in this case, but also to change the toolpath on the fly to whatever you might need it to be. So when you look at the overall challenges that you might have in additive manufacturing, we are trying to address quite a few of them. First of all, the pre-processing is of course very important, especially when you're talking about generating toolpaths for a 6-axis system. So we address everything from slicing to generating the non-planar patterns that you might be interested in for more complicated geometries. We also address, to a certain extent, the possibility to use multi-materials, to integrate robotic 3D printing into production directly, but also the process control and process prediction, which we will talk more about today. So in that sense, what we're trying to do is quite a complete view of it. And the idea is that at the end of this project, which will run during next year, the work will continue through a spin-off company or a startup company that we will form from the project partners, so that we can provide this as a solution to the industry. And with that, I will leave the floor to Sergio.
Thank you, Emil, and thank you, Anne, for the introduction. Can you see my screen?
Yes, perfectly, yes.
Great. So welcome everyone to this part of the webinar that focuses on polymer simulation in additive manufacturing. So what are the main motivations for doing simulation of additive manufacturing? And that's to avoid printing defects as maximum as we can. And with that, we can reduce scraping. If you look at the images here on the right, you can see this big part as a lot of warpage and buckling, as well as some cracks developing on the other side. So hopefully with the simulation we could avoid such defects. Furthermore, simulation can also be used to optimize material properties and to have a more efficient material usage. We can basically simulate many different configurations and optimize the material where we need it the most. Finally, simulation is a more important tool for large parts. The larger the part, the more important is the role of the simulation, because large parts obviously mean more waste in case anything goes wrong, and also more likely to have defects. So overall, simulating additive manufacturing can reduce costs and we can increase the quality of the parts. Okay, so where to start? And we start by simulating the thermal history. And why should we simulate the thermal history when we are interested in avoiding these defects and predicting the distortions? And the reason is that the residual stresses and distortions are caused by the thermal history. So the non-homogeneous thermal phenomena that occurs when we add new layers of material, they undergo heating and cooling. And furthermore, the simulation is also useful to obtain parameters that are otherwise difficult to use, to measure. So thermal simulations can be used as a calibration tool and as a validation tool. Here on the right, I have this example by my colleague. You can see that the elements are being added to the simulation, or as we call it, activated. And yeah, this is a fast forward animation, but you can see that the temperature is reduced after being printed. So we don't start by such a complex part. We start with a very simple structure, just 5 layers of ABS material printed on top of each other at 180 degrees, and this in a room temperature. So they are printed on top of a high temperature Teflon film just to avoid or to reduce friction with the surface. Okay, so if we yeah, if you want to look at the temperature field, we recorded the whole printing process with an infrared camera. And basically it looks like this in forward motion again. So yeah, you can see that the temperature goes from 180 degrees when it's printed to in the range of 130 seconds after, lower. So then we simulate this, and here you can see the comparison between what you saw before in the test and the simulation. So you can see that things look alike. We try to synchronize it as much as possible. So you can see that a new layer of material is added fairly quickly, and then wait for 30 seconds. We add another layer, wait again, and then we wait for a couple of minutes. So we're quite happy with these preliminary results. Looks quite good, but to make sure that the simulation is correct, we plot the temperature at a specific point in the center of the specimen on top of the first layer, and we plot the temperature from the test in black, the line in black, and from the simulation, the dashed lines. And so here is the printing of first layer. We add a new layer, the temperature goes up in this point. Then we wait, temperature goes down. We add the third layer, and there is a smaller bump in the temperature, and then we let it relax for a couple hundred seconds. So we can see that overall the results are satisfactory, and the simulation has reasonable prediction. Furthermore, we can see that when we change when we have a varying convection coefficient, so the line in orange, we can see that the correlation improves with the testing. So this is an example that this is a very difficult parameter if you don't, to obtain, and actually the simulation can help us. Yeah. So now to what we are interested, the distortions. So we need to generate geometrical distortion data based on thermal history. And in order to do that, we have two in-house models for residual stresses and distortions. One is path dependent, so the temperature will be accounted for, the stress simulation, linear elastic, and this is an approximation for polymers. The reason to use this model is that it runs fast, and it's also, so therefore it's good for development and conceptualization, but it's not time dependent. And then we have a second model that it's time dependent, so viscoelastic, which is much more representative of polymers. So it's more accurate, but in exchange it is slower and requires more material characterization. And both models can be made pure crystallization dependent, so can be used for thermosets or thermoplastics. And residual stress prediction and distortion during thermoplastic crystallization. So for this study, for proof of concept demonstration, we start with a linear elastic model, also path dependent, so require the thermal simulation. And here are the preliminary results. We have this specimen fixed on the left-hand side, And we can see that actually develops some high strains there. And here you can look at the displacements, and you see that they are higher in the pre-zone. And yeah, this is just the preliminary results to check the method. We didn't obtain all the material input for this, so we had to approximate them. But the results look in the right direction, and they just need to be validated. So that's it for the simulation of polymer materials in additive manufacturing. I leave the floor to Fabia.
Good afternoon, everyone. Thank you, Sergio. So the next step of this webinar will focus not on the model development, but on the following step of model development, which is model calibration. I will present some development that have been made for metallic additive manufacturing process simulation. Why trying to calibrate the model and spending some effort doing it? Well, the reason is quite simple. In order to model the thermal history in additive manufacturing, most of the time we have to use simplified models. The simplification concerns both the heat input, because we most of the time use an equivalent heat source, and it concerns also the heat losses, because we take into account convection and radiation, but especially for radiation, it's quite complicated to define the proper emissivity without any experimental data, because this is a coefficient that varies, for instance, with the oxidation or the roughness of the surface. So actually, the models that we use are quite simplified compared to the actual physics, and that's why the calibration is required, for instance, to derive the net power that is really absorbed by the material, or to take into account realistic heat losses. It's the same approach with the thermomechanical modeling. The physics is quite complicated. Elasto-viscoplasticity should be considered. And temperature dependency of mechanical properties is also important. But by doing that, the computation cost becomes quite a problem and an obstacle for running simulation on large geometries. That is why most of the time we try to replace this complex model with simplified ones. One of the alternatives is the inherent strain model, which is based on the simplification of the physics. So again, this simplification has to be compensated with some additional data, and this additional data can come from experiments. So one of the objectives of the project was to increase the model fidelity thanks to dedicated experiments, to make model calibration quite transparent for the end user, and suggesting an automated process for this calibration. And finally, to capitalize on all the experimental versus model comparison to gain more predictability. So how does it work? In the Softdream web application, actually there is a calibration module that is addressing both distortion model and thermal model. I will only present here the distortion model calibration. So the end user is asked to manufacture a dedicated specimen coupon with some dimensions that are suggested. Actually, this is a cantilever configuration that is asked, so that means that the substrate is only clamped on one hand and free to move on the other hand, and a wall is deposited on the substrate. So this coupon has to be manufactured, and the end user is still free to use a slightly different dimension because of some practical constraints. Sometimes it's not possible to build exactly the specimen as required. So some flexibility is possible in the calibration module. And if the dimensions are slightly different, then there is an automated generation of mesh and geometry corresponding to the exact dimensions that have been used for the experimental procedure. The other inputs are the process parameters that were used when manufacturing the coupon, the material that were used, and we refer to some material properties in the database. And finally, final input and very important input is the vertical displacement that is obtained on the manufactured coupon. And this input will actually be the key for calibrating the distortion model. So all this calibration is performed on the remote host server, and results, so calibrated model, are sent back to the web application and are then accessible to the user. So just an illustration of this. So an initial distortion model is first set up, and distortion is estimated. So a displacement, a vertical displacement of the substrate is estimated and is compared to the one that has been obtained on the manufactured coupon. The difference between both displacements is then an input for a correction box that will adjust the initially defined model and correct it in order to reduce the error between the measured displacement and the one obtained from the simulation. There are some iterations to do, and finally, the result of this is a calibrated model that is directly accessible from the web application. So just to summarize, here, the calibration of both thermal and distortion model is really compulsory, both for metallic, but also for polymer additive manufacturing process simulation. As I told you already, is because most of the time models are quite simplified compared to the physics, and the lack of data is to be compensated with experimental data. Calibration relies on simple specimen manufacturing, and depending on the type of calibration that we want to make, monitoring should be done on displacement or on temperature. The calibration approach that is developed in the project covers geometry and mesh generation, writing of the solver input file, post-processing of the results, and adjustment of the initial model, so calibration of the model. All the knowledge that is acquired thanks to calibration is really capitalized through databases. And the idea is progressively to get rid of this calibration step that would make the whole process much faster. The last section, the last part of this webinar will be now dedicated to the definition of manufacturing steps using distortion estimation. So how the distortion model can help choosing the right order in the manufacturing steps that are done. Again, a general overview of the tool. In the Softdream, as presented in introduction by Emil, there is a path planning tool that allows generating trajectories. This trajectory, combined with the geometry of the part, is used in order to build a mesh, so using a voxelization approach. And on the other end, the model calibration tool here is used just to use the proper model for the estimation of distortion. All this information is pre-processed, and the calculation is done regarding the part distortion. Finally, the results are extracted, and only a light result file is uploaded to the web application and is available to the end user. So now let's have a look at a use case. So on this picture, you can see a demonstrator part that has been proposed by Safran Landing System. This part is made of titanium alloy, and its dimensions are around 700 millimeters in length, 500 millimeters in width, and 200 millimeters in height. Here, actually, distortion estimation is used both for determining the substrate geometry that should be used, and also to define and to optimize the building strategy and the associated clamping strategy. Here, the choice that has been made is to use a symmetric configuration with the substrate in the center plane and actually two faces to be constructed, one that is called phase A and the other one that is called phase B. With using the distortion model, we've studied two scenarios. The first one is a scenario where one phase is completely built, so the phase A is completely built, and after we move to material deposition on phase B. So in this approach, the part is strongly clamped and no distortion issue is happening during no distortion issue is happening during the process. So the problem comes when the part isn't clamped. When the part isn't clamped, because of all the stress that has been generated in the part, it is clearly an obstacle to the following of the process, because there is around 11 millimeters of elastic spring back, and the deposition on phase B becomes impossible. So here we see that this first strategy is not the one that is really adapted. Another strategy is to alternate deposition on phase A and phase B. So in that case, the part is only clamped on its periphery. It's free to deform in its center part. And actually, by adding material alternatively on both sides, the stress is much more balanced and distortion is reduced. So by using that approach, we see that clearly distortion is clearly reduced, and it seems that it's compatible with the whole manufacturing of the part. So in that configuration, the distortion model can help optimizing a little bit more the process and determining, for instance, if several layers can be deposited on the same side before moving to material deposition on the other side. So this is an example of how the distortion model can be really a strong help in decision making regarding the manufacturing strategy of a part. So the perspectives regarding this work is, as I already told, going further in the optimization of the building strategy and trying to combine the distortion aspects and the manufacturing time aspects, so trying also to reduce the manufacturing time as much as possible. The developed approach will be adapted to polymer additive manufacturing process. And this full-scale demonstrator will be really manufactured in the next week. So it will be a way to validate the prediction from the model, confirm if the distortion trend predicted by the model is correct, and identify potential improvements for this distortion model. So this ends this last section on the use of distortion model for defining manufacturing strategy. And we will now conclude this webinar. So Sergio.
So thank you, Fabian. So a short introduction to the main concepts involving additive manufacturing simulation was focused on thermal history, and from that we generate distortion models. We design our polymer and metallic parts that are assisted by numerical simulation. We can predict the stresses, the distortions, and anticipate the formation of large or any cracks. So this has good accuracy for thermal analysis, and that is required to validate coupled thermal mechanical analysis. Fabien?
Yeah, regarding model calibration, so as presented, an automated procedure has been developed, and with the goal is to really improve the model reliability and to compensate for some simplifications that are made in the model. We've tried to make this step as transparent as possible to the end user, that is just giving some experimental results and is just then has the ability to use the calibrated model. A progressive enrichment of databases is also carried out, and the idea is to get some benefits, progressive benefits from the different calibration that are made, and in the future to remove this calibration step. The simulation of additive manufacturing processes is clearly seen as a strong help for decision making. It's a strong help when defining, for instance, when looking for a process window, because numerical design of experiments is a way to reduce the actual series of tests that are going to be made on the machine. So by just discarding some set of parameters that are not adapted. And also when defining a manufacturing strategy, as I've illustrated in the next section, in the last section, sorry, because it can be used to make some choices on the proper order of manufacturing for part.
The simulation is a great tool for us to use and to that help us to reduce time and costs, and the costs because not only we require less tests, but hopefully we have less scrapping, and we can have parts that are right at first time. So if you are interested in using simulation of additive manufacturing, please get in touch. Thank you for your attention, and we are open to questions now.
Thank you, Emile, Sergio, and Fabien for this really interesting presentation. We have indeed one question from a participant. So how relevant or representative is the calibration on a single and rather simple geometry for the actual distortion occurring in a more complex geometry?
Thank you, Anne. Yeah, it's a really good question. I didn't present it here, actually the double calibration, because I wanted to show the main, the general principle. Actually, it's not only a single specimen that is used, but actually two specimens, another one with a different shape, different geometry, to confirm the calibration that was, or the pre-calibration that was done on the first specimen. But the problem of representativeness of the calibrated model is still an open question, and the idea is progressively maybe to complexify the specimen, but trying to put maybe more features on it to be more representative. But this is something that we are going to work on in the following of the project.
Many thanks.
Was the question also meant for polymer simulation? Or?
So it was asked during the metallic presentation, but
Okay.
if information for polymer, you can add as well an answer.
Okay. Well, our structure is really rather simple. I agree with that. I would say since polymers will be isotropic materials, then we shouldn't worry. Like if you are able to capture the right distortion in one direction, you should be fine in the other directions. However, this was just the first, the simple example we could pick up, and will increase complexity. Thanks.
Thank you, Sergio. So we have another question who just popped up. Do you think the simulation of distortion is going to provide an indicator for the process?
Well, the estimation of distortion today is a tool, as I've presented here, is an estimation. So as it means that is less accurate than a full simulation, but it's a good tool to provide trend on the shape, the distorted shape that we're going to obtain, especially after unclamping the part. And it can discard some strategies just because generated distortion seems clearly not acceptable. So to me, it's a good indicator for the process. And well, it's always a compromise. The problem is the compromise to be found between the richness of the model and the computation time. So today we try to use quite simple model. Maybe we will show and see that they should be a little bit complexified to be more predictive. But yeah, this is something that we will learn progressively.
Yep, thank you, Fabian. So I think we don't have more questions for today. So many thanks again, Emile, Sergio, and Fabien for all the presentation and for answering the questions. So we have another one actually, which has come. Which software did you use to compute the final distortion? And did you use a fully coupled thermomechanical approach?
So regarding the distortion on the demonstrator, so the software is called VRFAC. The solver is Morpheo. And actually, no, it's not a fully coupled thermomechanical model. It's based on inherent strain simplification, where actually we only focus on mechanical response of the part for a given load, and this load can come both from thermal and plastic strain that is generated. So actually we impose some load and see how the part deforms in response, how the stress balances in the part and how it distorts. But it's not fully thermomechanical model just because it's much too costly, and we could not obtain results in a reasonable time. It will require days or weeks of computation before getting some data regarding distortion. It will be more accurate data because the physics is more rich, but it's not really usable in an industrial framework, at least today. Maybe this will change in the following years, but today is not really usable. So that's why we simplify the model, and we compensate the simplification with some additional data coming from experiment. So in some way, it's an hybrid approach.
Yep, thank you. We have another question on metals. So distortion in metals is partially related to the thermal field and partially to phase transformations occurring in the process. How is that accounted for?
Yeah, depending on the, it's right, depending on the alloy, on the material, phase transformation can be of first order or can be neglected. In the case of titanium, titanium alloy, it's true that phase transformation plays a role in the strain and the stress that is created in the part today, and that's why it's calibrated. Actually, everything is hidden in this inherent strain quantity. So there is both inside thermal aspects, phase changes aspect, and we do not try to identify in which proportion phase is acting or thermal part is acting. We just mix everything into this inherent strain concept and try to find what is the right inherent strain to consider. So from the physics point of view, it's not very satisfying, but from a practical point of view, it gives a good trend in an acceptable amount of time. So again, as I was saying, maybe a compromise has to be found, and this simple model could be complexified a little bit if the computation cost is not too much augmented. So it's a matter of compromise.
Thank you, Fabien. And I think we reached the last question. Just as a reminder, you will receive per email in 48 hours the link to this webinar, to the recording of this webinar. And we have our last webinar on real-time monitoring planned on Tuesday, the 24th of November, same time frame as today. So we really hope to see you in this last webinar, and thank you again for your participation, and thank you to all the speakers, Emile, Sergio, and Fabien. Thank you very much.
Bye.
Bye.
Bye.